Okay, let's unpack this. We are diving headfirst today into the mystery of interstellar objects, ISOs.
Right, these things that just swing into our solar system from, well, from somewhere else entirely.
Exactly. And they're really forcing astronomers to kind of rewrite the rule book, aren't they?
They absolutely are.
We're focusing today on the first 3 confirmed visitors. 1I Oumuamua, then 2I Borisov, and the latest one, 3I Tellus, which is, well, it's pretty strange.
It is. And our goal here, really, is to try and understand 2 main things. First, just why are these objects so incredibly different from each other?
Yeah, the physical diversity is striking.
And second, how their, let's say, unusual behavior is pushing scientists towards this really quite radical new classification system.
A system that actually, for the first time, has a way to talk about the possibility of, well, alien technology.
Explicitly, yes. It includes protocols for evaluating potential technosignatures.
Because the context here is huge, isn't it? We now know these things are basically planetesimals, leftovers from planet formation, flung out from other star systems.
That's right. Their existence proves there's this vast galactic population of them. The numbers are mind-boggling, maybe 10 objects just drifting through the Milky Way.
We're essentially living in a cosmic shooting gallery, and we've only just started noticing the bullets.
And the challenge, right from the start, was that the first 2 we found, Oumuamua and Borisov, were just completely different. Polar opposites.
Talk about confusing the picture immediately.
Exactly. It presented a real contradiction.
Okay, so let's start with the easier one first. 2I Borisov.
Right, Borisov. It showed up a couple of years after Oumuamua, and it was, a pretty well-behaved interstellar tourist.
Looked like a comet.
Looked like a classic comet. It had a visible coma, a tail. It was clearly active, shedding gas and dust.
And that non-gravitational push, the extra acceleration away from the sun.
Easily explained. You could see the mass it was losing, the outgassing. It matched the models perfectly. It also seemed pretty old, dynamically speaking, maybe 1 billion years or so.
So a standard comet, just from really far away. But there was something unusual about it, wasn't there? Chemically.
Ah, yes, the composition. That's where Borisov gets interesting. Your typical solar system comet has a fairly low amount of carbon monoxide, CO, compared to water. Maybe 4% or so.
Okay.
Borisov. It was incredibly rich in CO. The ratio of CO to water was closer to 1:1. Much, much higher.
And what does that tell us about its origins, where it came from?
It implies it formed in a very cold environment, deep freeze. That much CO suggests it was born way out in the coldest parts of its home star's protoplanetary disk.
Further out than our Kuiper belt objects, maybe.
Potentially, yes. It's like a frozen sample shipped in from the really deep storage of another solar system.
Okay, so that's Borisov. Weird chemistry, but fundamentally a comet.
Pretty much.
Then there's 1I Oumuamua, the first one. The total curveball.
Uh-huh. Dynamically younger, maybe only 100 million years old. And visually, it looked like an asteroid.
Just a point of light, right. Even in the best telescopes.
Exactly. Point-like. No coma, no tail, no hint of gas or dust. It seemed completely inert as it zipped past the sun.
And yet
it also showed that non-gravitational acceleration, that extra push.
Right. This is where the physics gets tricky.
Extremely tricky. We could measure this force pushing it away from the sun, definitely not just gravity. Normally you'd say, okay, that's outgassing, like tiny rocket thrusters.
But there was nothing to see. No exhaust.
Precisely. It was a ghost acceleration, a push with no visible engine. And the Spitzer Space Telescope looked hard.
What did Spitzer find? Or not find?
It basically confirmed the contradiction. To get the acceleration it had through normal cometary evaporation, Oumuamua would have needed to shed something like 10% of its total mass.
A tenth of itself.
Yeah. And Spitzer saw absolutely no evidence for that level of mass loss. Nothing close. It just wasn't happening visibly.
So it was moving without leaving a wake. That's weird.
Very weird. And there was another strange thing about its path. Its initial velocity, before it interacted with our sun.
What about it?
It seemed to originate from the local standard of rest, which, for you listening, is basically the average speed of all the stars nearby in the galaxy.
So it was just sitting still relative to the local star traffic.
Essentially, yeah, which is statistically quite unusual. Only about 1 in 500 stars or objects ejected from them have that particular kinematic signature. Most things are moving relative to the average.
Okay, that adds another layer of oddity. But we haven't even gotten to the shape yet.
Ah, the shape, the light curve.
How its brightness changed as it tumbled.
Exactly. The variation was huge. About 2.5 magnitudes, which suggests a very extreme shape, an axis ratio of maybe 6:1 or even 7:1.
So 6 or 7 times longer than it is wide. Or flat.
Could be either incredibly elongated, like a cigar, or extremely flattened, like a pancake or a disc. We just don't have common natural objects like that in our solar system. Asteroids and comets tend to be lumpier, maybe 2.1 or 3.1 at most, usually.
So extreme shape, ghost acceleration, weird starting velocity. No wonder the standard explanations started to fail.
They really did. People tried, They proposed exotic types of comets, maybe made of frozen hydrogen or nitrogen icebergs.
Stuff that would evaporate invisibly.
That was the idea. But those models have big problems. Like, how would something made of frozen hydrogen even survive millions of years traveling through interstellar space without just evaporating away completely? Or where would you get enough nitrogen ice?
Doesn't seem plausible.
It's challenging, scientifically. And that failure of conventional, even exotic, natural explanations, that's what led some scientists to consider something more radical.
Which ones?
That the smooth, continuous push it felt wasn't from outgassing at all, but from sunlight itself. Solar radiation pressure.
Just the pressure of light reflecting off it.
Yes. But for that to provide the measured acceleration, the object couldn't be a dense rock. It would have to be incredibly thin and have a large surface area.
How fast?
Like sub-millimeter thin. Essentially the characteristics of a light sail, an artificial construct.
Wow. Okay, so you have Borisov, maybe a weird comet, but understandable. And then you have Oumuamua, which is... well, it's potentially explainable by natural causes if you really stretch the physics. Or maybe it's something else.
That's the dilemma it presented.
And now, with new telescopes like the Vera Rubin Observatory coming online, we expect to find way more of these things, right? Not just a few per decade, but maybe one every few months.
That's the projection. A significant increase in the detection rate.
So we desperately needed a better way to classify them. A new scorecard.
Exactly. Which brings us to the Interstellar Object Significance Scale, or IOSS. You'll often hear it called the Loeb scale.
Like the Torino scale for asteroid impact risks.
Very similar concept. It's a 0 to 10 scale, but designed specifically for these interstellar visitors. And the crucial part is that it explicitly includes protocols for looking at potential technosignatures.
It builds in the possibility of technology from the start.
It provides a framework to evaluate that possibility scientifically, yes.
So applying this new scale, where do Borisov and Oumuamua land?
Borisov, the relatively normal comet, gets a level 0. Insignificant. Basically consistent with known natural stuff.
Okay, makes sense. And Oumuamua?
Oumuamua gets a level 4.
Level 4, what does that mean?
That's the critical threshold. Level 4 is defined as an anomaly meeting potential technosignature criteria. It flags the object as having characteristics, in this case, the non-gravitational acceleration without outgassing, plus the extreme shape that are hard to explain naturally and warrant closer investigation, including the tech hypothesis.
So it doesn't say it is technology, but it says it's weird enough that we have to consider it properly.
Precisely. It triggers a higher level of scrutiny.
And unbelievably, we already have another object that hits that same level. 3I Atsols.
Yes, the third confirmed ISO, Atsols, also currently sits at a level 4. And the anomalies with ATS are, in some ways, even more layered and statistically puzzling.
Okay, break down ATLS for us. What makes it a level 4?
Well, first, there's a potential size paradox. Early estimates suggested it might be huge, maybe 20 kilometers in diameter.
20 kilometers?
Yeah.
That's massive for an ISO.
It is. And statistically, that's a problem. If these things are just random chunks ejected from other systems based on the size distribution we expect, we should have found about 1 million smaller ones, like Oumuamua-sized, before stumbling upon something that big.
Like finding a blue whale before you ever seen a minnow.
Something like that. It implies an ejection rate of rocky material from other stars that might be way too high, exceeding the galaxy's mass budget. Now, the size estimate might be refined, it might be smaller.
But even if it's smaller, say closer to a typical comet nucleus size, like under a kilometer.
Even then, it has what we call an activity paradox. It does show some activity, a visible coma, some dust. But when astronomers looked closely with spectroscopy...
What did they find? Or not find?
They found no gas emissions, no water vapor, no CO, none of the usual cometary gases that should be driving the activity and creating the coma.
So it looks active.
Yeah.
But the usual engine for that activity is missing. That's the opposite of Borisov.
Exactly. What's causing the visible dust in coma if not sublimating gas? It's another mystery.
Okay, weird size, weird activity. What else?
The trajectory. This is maybe the strangest part. It's on a retrograde orbit, meaning it's going around the sun backwards compared to the planets.
Okay, that happens sometimes with comets.
It does, but its orbit is also very closely aligned with the plane of the Earth's orbit, the ecliptic. The chances of a random interstellar object having both a retrograde and near ecliptic orbit like that, about 0.2%.
0.2%. Pretty low odds.
Very low. But wait, it gets statistically weirder.
Good.
Its arrival time was remarkably synchronized. It made relatively close approaches to Venus, Mars, and Jupiter. The chance of a random object just happening to arrive at a time that allows for such close passes to 3 planets.
What are the odds on that one?
The cumulative probability is estimated at around 0.0005%.
0.005%. That's bordering on ridiculous for a coincidence.
It's highly improbable, let's put it that way.
And this leads to the spacecraft optimization idea?
Right. Some researchers pointed out another peculiarity. ATLS reached perihelion, its closest point to the sun, when it was on the opposite side of the sun from Earth.
Why is that significant?
Because that specific location is the optimal place to perform a theoretical maneuver called a reverse solar Oberth maneuver.
Okay, with that.
It's basically using the sun's massive gravity like a slingshot, but in reverse, to achieve a very efficient deceleration. You dive close to the sun, fire your thrusters briefly at perihelion, and you can shed a huge amount of speed with minimal fuel.
And doing it behind the sun.
Keeps you hidden from Earth-based telescopes during that critical braking phase. So the trajectory seemed almost optimized, both for efficient braking and for avoiding early detection from Earth.
Okay, so ATLS is racking up the anomalies. The size, the activity, the highly improbable orbit, and timing. It makes sense why it joins Oumuamua at level 4.
It certainly strengthens the case that we need this scale, and we need to be prepared for objects that don't fit neatly into our existing boxes.
Which brings us to the active search, right? The search for extraterrestrial artifacts, or SETA. It feels like this has moved from fringe theory to something scientists are actually planning for now.
It has, at least within certain scientific circles. It's important to note, government bodies like the Pentagon's ARO office dealing with UAP reports state they haven't found verifiable evidence of ET tech in those cases.
Right.
But for ISOs, the scientific community, or parts of it, are being proactive. They're not waiting for proof. They're designing the experiments and frameworks now.
And the main example of that is the Galileo project.
The Galileo project is key here, yes. It's a privately funded scientific initiative, and its stated goal is specifically to search for Oumuamua-like objects and also investigate UAPs using rigorous scientific methods.
So what are they actually planning to do? How do you search for these things?
They have a multi-pronged approach. One major goal is to design a rapid response space mission. The idea is when the Vera Rubin Observatory spots the next interesting ISO coming in,
which could be soon.
Could be relatively soon. They want to be ready to launch a small, fast probe to actually rendezvous with it. Get up close, take high-resolution pictures, see what it really looks like.
Wow, actually intercept one.
That's the ambition.
Yeah.
And on the ground, they're building sophisticated telescope systems. Not just standard telescopes, but arrays that record video, infrared data, radio signals, all simultaneously.
And using AI.
Using AI to analyze the huge streams of data in real time. The goal is to automatically filter out known objects, birds, planes, satellites, meteors, and flag anything that doesn't fit, anything truly anomalous.
And they're committed to open science, right? Making the data public.
Absolutely. Open data, transparent methods, sticking strictly to known physics, that's their mandate.
Let's back up a bit, though. Why artifacts? Why would some advanced civilizations send out physical probes instead of, say, powerful radio signals like in traditional SETI?
That's a classic question in SETA. There are 3 main arguments people make for probes over beacons: efficiency, security, and longevity.
Okay, efficiency. How are probes efficient?
Well, think about exploring, say, 1 million nearby stars. You could build a massive gigawatt-level radio beacon and blast a signal for maybe 1 million years. That takes immense energy.
Right.
Or you could launch a fleet of probes, maybe traveling at 10% the speed of light. The total energy cost turns out to be roughly comparable. But the probes guarantee information return about those specific systems they visit. The beacon just shouts into the void, hoping someone listens.
Okay, that makes sense. What about security? How are probes more secure?
A powerful radio beacon instantly gives away your location. The moment someone detects it, they know exactly which star system it came from.
Your home address is broadcast to the cosmos.
Exactly. A probe, on the other hand, is a messenger that doesn't necessarily carry an obvious return address. It allows for exploration while maintaining concealment, which might be important for a very advanced, perhaps cautious civilization. Military security, essentially.
Interesting. And the third reason, longevity.
Radio signals spread out and weaken over distance and time. Energy dissipates. But a physical artifact, especially if it's designed with self-repair capabilities, could potentially last for millions, even billions of years.
A true time capsule.
Precisely. It could preserve knowledge or information long after the civilization that built it is gone. That's why SETA often focuses on what are called Class 3 artifacts objects, whose mission doesn't depend on us detecting them. They're just out there.
And where would we look for such artifacts if they exist?
The most logical places are stable gravitational pockets within our own solar system, where something could remain captured for a very long time.
Like where?
Primarily stable orbits around the Earth, or the Earth-Moon system. This includes a large region in geocentric space, stretching out hundreds of thousands of kilometers, and also the Earth-Moon Lagrange points, L4 and L5.
Those points where gravity cancels out. Natural parking spots.
Exactly. They act like gravitational wells, trapping dust and potentially, maybe, ancient probes. There have been searches in L4, L5, but they're difficult looking for faint objects.
So putting this all together, what's the big takeaway here? What does this all mean?
I think the clearest takeaway is that we now have undeniable proof that our solar system is being visited by objects from other stars. This population of ISOs is real, it's massive, and it's incredibly diverse.
They're not just theoretical anymore. They are here. We're seeing them.
We are. And maybe the more profound point is that the anomalies we're seeing, particularly with Oumuamua and now 3 Atlas, are so significant, so hard to explain with standard models.
That they're forcing the issue.
They're forcing the scientific community to develop tools, like the Loeb scale, that are equipped to handle extreme outliers. Tools that allow us to scientifically evaluate the possibility of technology, even if it seems radical.
Again, not saying they are tech, but saying the data pushes us to rigorously test that hypothesis because the natural explanations are strained or just don't work yet.
Exactly. We've reached a point where some of these objects are classified as potential technosignatures simply because our conventional physics is exhausted trying to explain them naturally.
You know, the most fascinating insight for me, thinking beyond the "are they aliens" question, is what these objects tell us about other solar systems.
Absolutely. That's almost a guaranteed win, regardless of what Oumuamua turns out to be.
Yeah, like going back to Borisov. That high carbon monoxide content tells us it formed somewhere incredibly cold, way out in its home system.
Right. And since these ISOs are literally chunks ejected from other protoplanetary disks, studying their chemistry, their makeup, is like getting free samples delivered from alien solar systems.
It's a direct window into how planets form elsewhere, what materials are common, the architecture of those distant systems.
It's invaluable information. Understanding the composition of these visitors helps us understand the building blocks of planets around other stars. That knowledge is fundamental, whether the next ISO we find is a nitrogen iceberg, a weird comet like Borisov, or, well, something even stranger, like a light sail.
A truly cosmic delivery service, bringing clues about the galaxy right to our doorstep.